Hello and welcome to my JuliaCon 2022 talk. I am a postdoctoral appointee at Argonne National Laboratory. I do research on climate change and more precisely on the role of land-atmosphere exchange with the atmosphere. And my talk today is titled CUPofTEA, Community Understanding Platform of Terrestrial Exchanges with the Atmosphere. Here, community, the idea is to go from small groups, typically seen in academia, to a large group that we can see in open source projects. Understanding platform, there's two platforms behind this name. One is the backend platform, which is a raw code of this platform on GitHub. And the front end is a website, CUPofTEA.earth, that you can access today, which is a website where users can see interactive visualizations and results of analysis. And this is a work on terrestrial exchanges with the atmosphere. And to introduce you to this concept, climate models have different modules. They simulate the atmosphere, the ocean, the ice, and the land. And what about the land? The exchange between the land and the atmosphere. Everybody knows about climate change, but few know about Earth system models. Earth system models are the models that we build and use to make climate change prediction. And those models simulate the Earth's atmosphere, oceans, ice, and land. And for example, forests exchange carbon with the atmosphere via photosynthesis and respiration, and it also exchanges water with the atmosphere via evaporation and transpiration of plants. And in Earth system models, questions asked for the land is, for example, what is the future of vegetation on Earth? Are we going toward more deserts or more forests on Earth with climate change? What will happen to soil carbon? For example, what happens to the carbon which is in permafrost? And what will happen with soil water, with change of precipitation, atmospheric water demand, vegetation, and conductance of vegetation. So, look at the figure on the right here. Climate models, as well as observations of exchange between the land and the atmosphere, have both been developed over the past 70 years and started in the 1950s. First, climate models only had atmosphere model, and then in the 60s oceans were added, and only more recently in the 2000s land atmosphere exchange were added to those Earth system models. And in parallel, flux tower measure exchange between ecosystems like forest and the atmosphere. The principle was developed in the 50s, but only deployed in the 80s, where first flux towers were deployed. And then in the 90s, regional networks were created. In the 2000s, global network, FluxNet, was created. These are half-hourly data of exchange between forest and atmosphere of carbon and water. And in 2010, standardized processing was developed so that all those data streams are processed in the same way and provide similar outputs that can be analyzed with the same code. So this is the past, and today we are in the 2020s. And where are we going now is the point of this figure. So for climate models, there is a need today to integrate all those data we've collected into those models, and that's a concept that is called here ModX, as in model and experiment merging. We have to learn how to leverage AI and machine learning to create better climate models, consider better scaling, going from very small scale, like enzymes, to Earth scale. And as computer develop, resolution can be developed for those climate models. For measurements in 2020s, I believe that there is a need for a versioned and open source analysis and visualization across scales, so from leaf to plant to forest, for model and for observations. So again here, what are the challenge of 2020 for the land module of Earth system models? Challenges are that currently data outpace model development. There's so much data available that it's hard for models to keep up with all this data. There is a need for more cross-disciplinary science, and there is a need for empiricists or experimentalists to collaborate and work with modelers. Currently, you often have empiricists on one side and modeler on the other side, and they don't collaborate much. So why are these challenges existing? So recently, in the year 2000, there's been a very fast development of in situ, so in the field, sensors and remote sensing. So more and more we've got continuous observations of things like soil temperature, carbon and water fluxes, and remote sensing, and so on. And also, science is currently made mostly by small teams of very specific fields, and they don't collaborate with other fields. But this is a problem because the Earth system is a result of interactions between all fields of Earth science. So typically, the way scientists do work in ecology for experimentalists is to design an experiment to test a hypothesis, and then you're going to collect data for different treatments and do statistical analysis on this data, and then write a manuscript and publish it in a peer-reviewed journal. And then once your data and paper is published, you move on. But things are changing in 2000s for land ecology, for Earth system models application. With the development of in situ sensors and remote sensing came the development of regional, national, and global standardized database, which allow meta-analysis, so analyzing all those giant data sets across the globe, and also all those data can be compared with model to both develop the model according to what we can learn from data, and also develop the experiments according to what the model needs. So the framework, collect your data, analyze it, and move on, may not be adequate anymore because data is just continuously being measured, and you can't always just do your analysis and then you're done, since data keep being measured and changing, methods are changing, and so on. So recently among the community of land ecologists, there is a call for cyber infrastructure to change a bit how things are done. But this is not easy to do because ecologists are not developers. So more and more ecologists have to learn how to code and be programmers, but this is not our primary formation, and so building and using this cyber infrastructure is a challenge for ecologists. So ecologists ask for, and scientists in general, good practices, such as sharing the data you collect, sharing the code you use to generate your analysis, and some go beyond this and create package to allow easy reproduction of analysis with similar data. But I would say this is less than 1% of scientists because, again, ecologists are not developers and creating a package is not something we're taught as ecologists. But it is important and some people do it, and there is more and more call to do more programming work like creating package to allow dissemination of the analysis tools we do and create. And this is where CUPofTEA comes into play. I see CUPofTEA as being the next step beyond creating a package that allows to reproduce your analysis. CUPofTEA is meant to, you create the package, but those packages are used to automatically analyze new data. So the idea is to use open source developer practices for community versioning and automated analysis of databases. So those packages would be run automatically as new versions of those databases are created. So this would allow to for your analysis to stay fresh and up to date. So as new data arrive, which can be new sites, new years, or also new methods, the data we collect is not, we make assumptions and so on, it's not perfect data, and sometimes we develop new methods for this data, and so the analysis will need to be recreated on the same data set because it has changed with new methods. And those analyses can be tweaked, etc. So having a continuous integration on analysis would be great for the community. It would allow to facilitate communication and collaboration among scientists. It would motivate scientists as well because you can see live development and progress, and you would continuously build a puzzle as a community and put all the pieces together right there on the platform, as opposed to have many manuscripts which recognize each other, but they're not all in the same place at the same time. And also students could contribute more easily by working on a small piece of the puzzle. So this slide here shows some advantage of open source over academia. And I am not calling open source to replace academia, but rather to complement academia. Open source allows more easily for large groups to collaborate. So you can have hundreds of people collaborating on a Git repository, and the progress of new code added is live, as opposed to the slow process of peer review publication that can take years to communicate simple results. Instead of publishing and moving on, you have continuous integration of your data and code and versioning. Students can contribute. This is an organization work as opposed to a publication, which is mainly linked to the first author. Instead of having a one-time peer review with a few reviewers, you have a continuous numerous peer review. Open source is free. The public and scientists can easily access if you have a front end communicating what you're doing, and you can have more interactivity on that front end as well. So why now and why Julia? So why only now? Scientists, as I said, are not developers. We write stories, we publish manuscripts. So it wasn't our main goal to create platforms like that. And distributed version control is recent, as opposed to, as I said, climate models and land atmosphere exchange, which were developed in the 1950s. Git and GitHub have only been created in the year 2000. Why do I think that Julia is optimal for such a project? Julia has an easy package manager, and we need things to be easy because we're not developer. It has a simple syntax. Currently R and Python are popular for empiricists, but Julia is just as simple as those languages. And Julia is fast. It's fast enough to write a system model in Julia. So currently our system models are all written in Fortran. And there is a new project, Klima, which will be written completely in Julia, so it is possible. And Julia is built for modularity. So for building this puzzle where you can work on different pieces separately, Julia is perfect. It will take time to teach new generation of scientists to learn those basic of developer practices, but it will happen. Okay, this is a complex slide. I will spend some time on it. And this is a utopia version of my vision of this platform, CUPofTEA. The goal of this platform is to centralize and continuously integrate fair land atmosphere exchange data, but not only data, also models, codes, figures, and interpretation. So currently, FAIR principles mostly apply to data, but here the idea is to apply those principles also to code, figure, and interpretation, make communication and collaboration easier, generate a true community code base, and make community analysis tractable with versioning. So this is how I envision CUPofTEA. I see one place where you can download all sorts of land atmosphere exchange database. So there's database of in situ observation. For example, FluxNet is a global database of land atmosphere exchange of carbon and water. COSOR is a global database of soil respiration. SubFluxNet of subflux. TRI is leaf properties, and so on. So these are in situ database. Remote sensing, such as MODIS, GRACE, Landsat, and so on, and a system model database. So all those databases are huge amounts of data and effort, and they are usually hard to, they are found separately. There's no centralization of all those databases. But it would be great to have at least a place where you can have links to find them and download them. And you could have a user interface to play with this. So once you have all your database in one place, you can link them to what I call here a code base. So code base would be one place, so for example a Git repository, or the GitHub of CUPofTEA, which contains analysis code of many analyses that run with one or more of those databases. And so every time databases are updated, as I said, with new site, new year, or new methods, then the continuous integration workflow download the new version of those database and rerun the analysis of one of those codes. And as those codes are run, they generate visualization, text files of analysis output, etc., that you can all find on a website providing interactivity to look at different visualization or download different data file and so on. And then, so this would be the interactive web visualization and analysis output base. And then scientists need to interpret those results, and with different versions of those outputs can come different interpretation that could be updated by the community, maybe every year or something like that. So this is very ambitious, and this is an utopia. However, it is completely possible to build something like that, and that's what we try to show with CUPofTEA proof of concept. So this is how it works. CUPofTEA is a Git repository that I show here. So this is just folder. In this folder, you've got an input folder containing all your inputs. So here I just have 3 databases in this proof of concept here. So FluxNet, as I said, is a database of flux tower collecting exchange of carbon and water. So you can see there's 200 sites all around the world of this data. And for each location, you've got data files of exchange between a forest and the atmosphere, exchange of water and carbon every half hour. So all those files are standardized and processed, and you can do your analysis on those files. I'm opening one here. There you go. So this is what those data files look like. You've got tens of thousands of lines corresponding, each one line is 1/2 hour. And then you've got many rows of data such as respiration, photosynthesis, evaporation, and so on. So this is just one data set. There's many data sets globally. That's one database. And then you have many databases. So this is all your input file. And you have in situ data, remote sensing data, and model output databases. So these files are ignored by Git because they're too heavy in size, and also they have different licenses. They're hosted locally. So if you just have a few databases, it can be hosted on your personal computer. And if there's too many, you have to remotely host them on a computer that can handle the heavy size of this database. And you need a script to check if you have the latest version of this database, and to download a new one if available. So this is it for the input. And then you have a function folder which would gather all sorts of analysis done on different databases. And those analyses, they create all sorts of outputs and visualization and so on. So this code is hosted on GitHub. And here's the GitHub organization, and here is the Git folder that I just showed you. And input is not there, but you have functions, and those functions have to be pretty short and as modular as possible, so that you can work on pieces of this analysis and very pinpoint what you want to work on and what you want to change. This is, for example, calling many scripts and packages to generate figures that I will show you on the front end. So on the front end, when you run your code, which uses input, it creates figures and outputs that you can visualize and download on the website. So this is the front end. So that's this website, CUPofTEA.earth. You can go on it on your web browser. It currently is just a proof of concept stage. You've got 3 menus. One of them here shows you an interactive model visualization of predicting CO2 emission by soil as a function of soil temperature and soil moisture. And it is interactive here. You can change the temperature and the moisture and some parameter of your soil and so on, so that you can explain what the model do. And this is important to me because easy communication with other scientists for cross-disciplinary project is important. And then this model has been parameterized of all the global sites, so the 200 sites of flux towers that I mentioned and showed you before. So you can see here different response of CO2 flux responding to temperature and moisture at different locations in the world. So this is here on top using ecosystem database, and here on the bottom it's fitted to a soil respiration database. So I'm using 2 databases. And you can see here that some data sets were faulty, they were having issues. And this is highlighting why you need versioning. So these issues will be corrected in the future version. And so in the next version, there won't be those problems anymore. And so we make progress little by little. And as soon as the new version will be available for this database, a new version will be available here. This is another visualization example where you can see spatial temporal variability of soil moisture, soil temperature, and soil respiration. So all this available on your browser. And the idea is so that these visualizations are updated live as new data is collected and as new sites are available. So this was a proof of concept. Currently, CUPofTEA uses many packages, and for example, it uses Mackie and GSSF to produce those web figure. It uses Franklin to create a website, data frames to play with those data sets, a Unitful for the modeling, accounting for units, etc. As final thoughts, the idea of CUPofTEA is to leverage developer practice for ecologists and going towards a community effort for continuous integration of global land database and models understanding. I really think that CUPofTEA or a similar framework need to happen for our community to make progress. And I think it will take time to initiate such efforts, a few decades, because as I said, new generations of scientists need to be formed to do this. But in research, we have time, and it is okay to be ambitious and think about effort that needs decades. And Earth system models and research on land ecology is here to stay. Even if we fix climate change, we will still use Earth system models to understand future ecology. And also, these models are also valid for other planets. And so, this is where our community is going. Thank you.